Example 5.9. Problem. A block with a mass of 5 kilograms is attached to a horizontal spring with spring constant 400 newtons, as in figure 5.21. The surface of the block rests upon is frictionless. If the block is pulled out to 5 centimeters and released, find the speed of the block when it reaches the equilibrium point, and find the speed when it reaches 2.5 centimeters. And part C, repeat part A if friction acts on the block with coefficient mu sub k equals 0.150. So here's the idea. First, we're going to pull the mass out here and then let it go. And we're going to find out how fast it's going when it reaches here and how fast it's going when it reaches here. We are also going to find out if we add friction to the block and release it from the same point, how fast is it going when it reaches here, and how fast is it going when it reaches here. So, before we figure out the velocities of each of these places, let's figure out how much energy is in it. I've written down one of the forms of the conservation of energy equation over here. Energy initial plus work non-conserved is equal to energy final. I'm going to break that down into potential energy final plus kinetic energy final, potential energy initial plus kinetic energy initial, plus the work non-conserved. So in each of these cases, our kinetic energy initial is going to be 0 because we have stretched the spring out to its furthest point. So we can eliminate that, and we will, I think, to have we want the initial potential energy of the spring to be kind of prominent, so we'll go ahead and we want that value to be positive, so we'll move that over here, and then we'll subtract potential energy of final of the spring. We want that to be negative, because that'll be kind of our change. It'll be in a negative change in potential energy, so that'll be plus work non-conserved equals, and I subtracted that off, so it is kinetic energy final. Finally, I'm going to take this and just call it work conserved plus work non-conserved equals kinetic energy final. And I think that will be the mode of this equation that will be the most helpful in this case. So we're going to consider the situation of what energy is stored in the spring in each of these cases. So the energy stored in the spring is 1/2 kx squared. So I'll mark this 1/2 kx squared here. And as I go down here, it's smaller. As I go up here, it's bigger. Alright, and here's the essence of what the problem asks for. First of all, we're setting mu sub k equals 0. It's a frictionless table. And we want to know what is the work conserved plus the work non-conserved at x equals 0. So we're taking the mass and pulling it to x2. We're letting it go. And then we're finding out what is the work done by the spring at that point. And the answer to that is 1/2 kx squared. It's the area of this whole triangle. How about at x1? We do the same thing. We let the mass go here, but we find out what the energy is in the mass at that point. Okay, so the work done, or the kinetic energy, will be 1/2 k. Oh, sorry, this was x2 squared. x2 squared, because we pulled it out to x2. And this one will be 1/2 k x2 squared minus 1/2 k. Oh, shoot. Anyway, let me actually. 3, 2, 1. Okay, so when we let the mass go from here all the way to here, the kinetic energy in the system should be equal to the original potential energy of this, which would be 1/2 k x2 squared. So delta k, or kinetic energy final, will be 1/2 k x2 squared. However, when our final x is x1, it will go from here, where the energy is 1/2 k x2 squared, to here, where the potential energy is 1/2 k x1 squared. So kinetic energy final in that case is 1/2 k. And you can just write this as x2 squared minus x1 squared. Or you can write it out with the 1/2 k x2 squared minus 1/2 k x1 squared. Okay, and then here, with mu mg is not equal to 0, kinetic energy final will be equal to the same thing we had up here, the area under that curve, 1/2 k x2 squared, minus, and this is the energy that is removed by friction, it'll be 1/2, or it'll just be mu mg, that's the force, times x2. And for the other one, where we're just going halfway, it'll be the area of that part minus the area under that part, which will be kinetic energy final equals 1/2 k x2 squared minus x1 squared, which is the area of this section there, minus mu mg times x2 minus x1, which is the area of this rectangle right here. So doing some calculations, 1/2 k x of 2 squared, the area of that whole triangle there is 0.5 joules. And then 1/2 k x1 squared is the area of this triangle here, comes out to be 0.125 joules. So the area of the segment here is 0.5 minus 0.125, or 0.325 joules. And the work done by friction is the force of friction times the distance. Actually, I put in x2 there. So it's 0.368 joules for the whole distance, or half of that for half the distance, 0.184 joules. So for part A, the final kinetic energy was the total area of that triangle, which was 0.5 joules. For part B, the total kinetic energy was the area of that part of the triangle, which was 0.375 joules. The answer to part C, part A, was the entire area of that triangle minus the area of that rectangle, which was 0.1325 joules. And for C dot B, we take the area of this part of the triangle minus the area of the shaded spot here minus the area of the shaded spot there, which is 0.191 joules. For the final velocity, we are going to use the equation 1/2 mv final squared equals kinetic energy final, which will be 2 kinetic energy final divided by the mass and the square root to get v final. Okay, so we have the final kinetic energy in each case, and we have the mass. So I'll type in equals square root of 2 times the kinetic energy divided by the mass, and copy that down, and we'll have all of our velocities for part A, B, C dot A, and C dot B, and those are all in meters per second.